Hi, and welcome to H1.4 Angular Variables and Tangential Variables. In this lesson, students will be able to use rotational kinematic equations to solve for missing variables given tangential or linear variables. And we're going to do that by using what I like to call Switcheroonie Interchangers. Sometimes you want to switch from rotational physical quantities to linear physical quantities. Just switch it up. It's that easy. So we already saw this is the arc length formula, and you can use this to switch. It's a switcheroonie from a linear variable. This S is measured in meters. It's the arc length. How many meters is that arc? How long is that arc? And you could actually use that to translate into, we did a problem where the wheel rolls along and the arc length that it rolls through is equal to the distance that it travels. If you remember, we did something like that. So that's like the linear variable measured in meters. And then this is our rotation variable, the physical quantity. So all you have to do is just multiply by the radius. If you're given the angular displacement and you want to know the linear displacement, you just multiply by the radius. Sweet. It's like you switch it from rotation into linear by just multiplying by the radius. So here's that example. It says a car tire has a radius of 0.5 meters. How far does the car travel if the tire makes 2 turns? We want to know how far that is. Well, we know the radius is 0.5 meters, and we know it goes through 2 revolutions, but we have to convert that to radians if we are going to use our arc length formula. Remember, this formula, you need to be in radians, okay? So you just plug in, the radius is 0.5 times 2 revolutions, or 4 pi radians, and you get a distance of 6.28 meters. So the distance around the circle twice is 6.28 meters, and that translates to 6.28 meters as you travel linearly without slipping. You assume the tire doesn't slip. So what about angular velocity and angular acceleration? We've already seen the S equals R theta equation. How do you switch between those and their linear equivalent? If you're given the angular velocity and you want to know the tangential velocity, it's the same thing. You just multiply the rotational physical quantity by the radius, and you're given the linear or the tangential velocity. And same with the angular acceleration. You multiply the angular acceleration by the radius, and then you get the tangential acceleration. That's it. Oh, you want me to prove it? Okay, let's prove it. Let's derive the formulas there. So if you have this is our definition of a radian. It's the arc length formula. And let's say we just divide one side by t. Well, whatever you do to one side, you have to do to the other side in order to make the equation still equal. So this is all good. It's still an equivalent thing. And what we can say is, we said before that this arc length is really a measure of your distance around the circle. And we know that the distance divided by the time, or the displacement divided by the time, is equal to your velocity. And then does this look familiar? Theta divided by t is your angular velocity. So we just substitute in those values, and we have a new Switcheroonie interchanger. Your tangential velocity is equal to your angular velocity times the radius. Another switcheroonie. It's very similar to this one. You just take your angular physical quantity, multiply it by the radius, boom, you have a linear or tangential physical quantity. All right, so there's actually 2 ways to derive the one for the angular acceleration. We could do a very similar thing where we divide both sides by t, and your change in your velocity over time is your acceleration, and your change in your angular velocity over time is your angular acceleration, and we just substitute in those values again. Boom, another Switcheroonie interchanger that we can use to go from linear to rotation for your acceleration. A different way we can derive this in a different way. I mean, we're still going to get to the same equation at the end, the same Switcheroonie interchanger for the acceleration, but let's have fun doing it a different way. Why not? So we already know the definition of the acceleration is your change in velocity over time. And now let's put this over there and over there. And now we have, instead of the tangential final velocity, we have r times the angular final velocity. So we're just substituting in there. And then we could take the common term out. So we take the radius out. And then what does this look like? That is your angular acceleration formula. So we just plug this in for this whole deal. And guess what? It's the same exact equation. I was just showing a different way to derive it. So yeah, that's a nice Switcheroonie interchanger there. Beautiful. But what about the units for these things? In previous lessons, we were like, oh, as long as the units all agree, you can use it. Well, let's see. The angular displacement needs to be in radians, and the angular velocity needs to be in radians per second, and your angular acceleration needs to be in radians per second squared. Why? Because a meter is equal to a meter. This radian is kind of like unitless. And what is a meter times a unitless thing divided by a second? It's just a meter per second. And then again, we have a meter times an inverse second squared, you could think of it. So yeah, they need to be in radians in order to use the Switcheroonie interchangers. You wouldn't be plugging in a revolution per second squared or a degree per second squared for this interchanger. All right, so all of these, they need to be in radians. So where are these Switcheroonie interchangers on the reference table? I give them to you all right over here, and as we can see, they are in the section that we've been saying, oh, these need to be in radians. All right, so all of those are given to you right here. So here's a little critical thinking question for you. Which position has the greatest tangential velocity, and which position has the greatest angular velocity? This thing is going to rotate this way. Take a look at the blue, orange, and pink places. I'm only going to rotate it once. So think of the greatest tangential velocity and which one has the greatest angular velocity. Let's take a look here. Wow, look at that. Really nice. Okay, so which one of those like moved the fastest tangentially? And which one had the fastest angular velocity? Pause the video and think about it. Think critically. Did you pause the video? I'm just going to give away the answer now. You didn't? Come on, pause the video. Let's see. All right, well, let's think about our arc length for each of these. For the blue one, it's a very small arc length. You're not covering that much distance. For the orange one, it's a little bit more. So you're covering more distance in the same amount of time. Did you see how this rigid object moved as one? It's not like you had different times. The time is the same, so I made that like the same size font, but the arc length is larger. So you're covering more distance in the same amount of time. That means you must be going with a greater tangential velocity. And then the pink arc length is the largest of all. You have to cover a huge distance in the same exact amount of time, so you must have a large tangential velocity. If you want, you could rewind the video and watch the rotation happen again and see if you could see this one's like kind of moving slower compared to this one. You could think of it that way if you think of the tangential velocity. But which position has the greatest angular velocity? Pause the video and think about that. Maybe it's a weird question to ask because they actually have the same angular velocity. They're rotating around as one whole unit. So they go through the same angle, 90 degrees. Okay? So in 90 degrees in the same amount of time, you're going to have the same angular velocity for all of those. Very nice. So that's some good questions there. All right, how about this question? It says a helicopter blade has an angular speed of 6.5 revolutions per second and an angular acceleration of 1.3 revolutions per second squared. For points 1 and 2 on the blade in the picture shown, find the magnitudes of the tangential speeds and the tangential accelerations. If you want, you could pause the video and try this one out on your own. There is a little bit of a trick in there, so don't get caught up on the trick. Okay, so the trick is these are given to you in revolutions. We need radians in order to go from an angular speed to a tangential speed or velocity. And to go from an angular acceleration to a tangential acceleration, we need radians here, not revolutions. So let's start by writing our givens down. The angular speed is 6.5 revolutions per second. I'm going to write it like that so that we can do our unit conversion. I'll do it right away. All right, because I know I want to be in radians. Now, revolutions is in the numerator here, so I'm going to put it in the denominator there, and I want to go into radians. So these will cancel out, and we know that 1 revolution is equal to 2 pi radians. So you could leave it in terms of pi if you want. That'll be 13 times pi radians per second. Like this is a number here, 13 times pi. Okay. The angular acceleration is 1.3 revolutions per second squared. We don't want revolutions. We want it to be in radians. So we actually multiply by the same exact conversion factor because the revolutions are on the bottom so that these cancel out. And it's 2 pi radians. So 1.3 times 2 is 2.6 times pi radians per second squared. Now they're looking for the tangential velocity at point 1, which we can show like this. This is V1. The tangential acceleration at point 1. So this thing is speeding up. It's getting faster and faster and faster. And this tangential velocity is speeding up. It's getting faster and faster and faster. In the next lesson, we're going to talk about, you might be thinking, is that the same as the centripetal acceleration? No, it's not. When we did centripetal acceleration, we did it in uniform circular motion, where the speed stayed the same. Now the speed is increasing, so you do have some tangential acceleration in addition to your centripetal acceleration, and you do have a, let's see how we're going to write this. So there's 3 types. I'm going into the next lesson a little bit, but just in case you were wondering, what the heck is that tangential acceleration? So you have an angular acceleration. Now I was thinking about how I'm going to draw the direction of that arrow. This is a counterclockwise rotation, so it goes out of the page, and you use a dot to represent an out of the page. You would use an X to represent into the page. But again, I'm getting a little ahead of myself, but it's kind of fun thinking about all the different types of acceleration we got going here. And it all comes from the fact that now we're speeding up in the circle, whereas before we did uniform circular motion where it was the same speed. Wow, what a tangent that was, huh? Tangent, you get it? So this is back to business here. This is what we're looking for. All right, and we're going to use those Switcheroonie interchangers now that we have everything in terms of radians. So the first one, the tangential velocity, you just do r times your angular velocity. Now this is for the first point, okay? So we could plug in VT1, the radius. Oh, I didn't even write down the radius. R1 is equal to 3 meters according to that picture. R2 is equal to 6.7 meters, okay? So this is 3 times 13 pi. And your tangential velocity is 123. What are the units for tangential velocity? What do you think? It's velocity. It's just meters per second, okay? All right, so now we have, I'm going to give myself some space here, I think. And I'll solve for the accelerations in green to kind of differentiate it. So again, we got our Switcheroonie interchanger. The tangential acceleration is equal to just r times alpha, okay? R times the angular variable. And again, we get this tangential acceleration because our tangential velocity is getting larger because we're spinning faster and faster due to this angular acceleration. Pretty cool stuff. Pretty cool stuff. All right, so let's keep going, Mr. Nangle. Come on, let's go. So the tangential acceleration is 3 times your angular velocity, 2.6 pi, 2.6 times pi radians per second squared, and you get 24.5 meter. Oh, I gave it away. What is the units for tangential acceleration? It's a meter per second squared. Sometimes people want to say the radian per second squared for that one, but it's not, okay? So then we have the 0.2, which is further out on the blade. So what would you expect the tangential velocity to be? Would you expect it to be the same, greater, or less for a point that's further out? Let's see what we get. So again, you got the Switcheroonie interchanger. This time for 0.2. You substitute in your values. Remember, it's a larger radius now, but we're moving with the same angular velocity like we talked about on the previous slide. And you get a value of 274. What are the units again for tangential velocity? It's meters per second. So hopefully you predicted that this would be a greater velocity since it's a larger radius. All right, let's do the acceleration. Again, this is for 0.2. Let's substitute in the values, and you get 54.7 meters per second squared. So not only are you moving faster tangentially the further out you go, but that acceleration is also greater the further out you go, the tangential acceleration. Pretty fun stuff. All right, so we got those Switcheroonie interchangers. Main idea, don't forget to make sure it's in radians when you're doing any of these switcheroonies. Okay, like this, or this. Great. Anyway, that's about it. Thanks for watching and have a great day.